Welcome to the third lecture of this week. So far we have seen analysis of free vibration of laminates using Navier type solution. Now today we will see a different problem where Navier type solution is not possible. So we will do Levy type solution, and we have seen that while doing static analysis also. So we have a laminate, and this laminate is cross ply laminate. Symmetric cross ply laminate. It is in X, Y, and we have two opposite edges simply supported. So this is simply supported, this is simply supported. This is dimension A, this is dimension B. So these two edges are simply supported, and these two edges can have any other type of support. They can be clamped, they can be free, they can be fixed free, and they can be simply supported also. And this is symmetric cross ply laminate. So it is symmetric cross ply. So we will do Levy type solution for this. Now we know that the differential equation governing this behavior is dxx into del to the power 4 by del x4 plus twice of dxy plus 2 into dss into del to the power 4 divided by del x2 del y2 plus we have dyy del to the power 4 del 4w by del y4, and then we have the inertia terms, and for that we have plus I0 into del 2t by del wt and minus I2 into del 2 w double dot by del x2, and then plus del 2 w double dot by del y2, and since we are using dots to show the time derivative, we can just write this as w double dot also, and that's equal to 0. So when here in plane inertia terms are dropped, so in plane inertia terms or I can write inertia terms corresponding to I0 inertia terms corresponding to U0 double dot V0 double dot, they are dropped. Okay. Now the boundary condition says that at x equal to y equal to 0 and y equal to b, we have w equal to 0 and we have my equal to minus of dxx dxy into del 2w by del x2 plus dyy multiplied by del 2w by del y2 equal to 0. So, and we don't know right now we don't know anything about x equal to 0 and x equal to a. Actually we know, but we are not going to apply that. So, we will keep it free. That means later on right now it is free to take any boundary condition, and later on we will take the appropriate boundary condition. So, the assumption that we make is, assume if we follow what we did in the static analysis, we had w as a function of x, y, and the assumption was n equal to 1 to infinity, and then along the x it remains a function of x. We don't give it any form along the y because of the boundary condition. We keep it sin n pi y by b. Now in static analysis, this w was function of only x and y. Now this is a function of time also. So t is there, and for that we write it as e to the power I omega t, assuming harmonic solution. So w is a function of x, y and t, and so we are writing it as a function of x, function of y and function of t. Now function of y and function of t is known to me, but function of x I am keeping it free right now. Now here we can see that this satisfies this boundary condition. If I put the value y equal to 0 and y equal to b, the entire term becomes 0, and then if I put y equal to 0 and y equal to b here, again it becomes 0. Now if I try to recall from what we did in the static analysis, Levy's solution, we made some assumption like this. Only thing was that the time dependence was not there, and then we put this assumption in the differential equation, and that gives us an ordinary differential equation in x, and then we solve the differential equation, and the solution has some unknown constant associated, and those constants are evaluated with respect to the boundary condition given at x equal to 0 and x equal to a. So the same procedure we will follow now. So this is Levy's solution. Now if I put this in the differential equation, we get, so putting the approximation in the governing differential equation, we get the following. So if I put it here, we get dxx multiplied by d4wn by dx4. So here this wn is a function of x only, so instead of writing partial derivative, we are writing d. The rest of the terms will become common, so we will take care of that later. And then we have 2 into dxy plus 2 dss, then we have minus n square pi square by b square, and then we have d2 wn by dx2, and then we have plus dyy n to the power 4 pi to the power 4 by b to the power 4 wn, and then we have minus omega square I0 multiplied by wn, and then we have plus I2 d2 wn by dx2 minus n square pi square by b square into wn, and this multiplied by omega square, and everything multiplied with sin n pi y by b into e to the power I omega t, and this the summation goes from n equal to 1 to infinity, and that's equal to 0. Now we know that this cannot be 0, so whatever we have inside this second bracket has to be 0. So now we can write this as, so for each n we get an equation of this form, dxx, if I just arrange the terms little bit, dxx multiplied by d4 wn by dx4 plus I2 omega square minus 2 dxy dxy plus 2 dss plus 2 dss, and then we have n square pi square by b square and finally everything is multiplied with d2wn by dx2. So n square pi square by b square, and we multiply this with d2wn by dx2, and then we have finally dyy n to the power 4 pi to the power 4 by b to the power 4 minus omega square I0 plus I2 n square pi square by b square, and this is multiplied with wn, and that's equal to 0. Now for simplification, let's call this term as small p, let's call this term as small q, and then let's call this term as small r. So we can write the same differential equation as p d4 wn by dx4 plus q d2 wn by dx2 plus r wn equal to 0. Now we have seen before, for solution of this type of equation, we assume a solution of this form. So let's assume the solution of this equation to be wn as a function of x equal to c into e to the power lambda x, and then if I put everything in this differential equation, we get an algebraic equation of lambda. So what we get is p multiplied by lambda to the power 4 plus q into lambda square plus r into c e to the power lambda x. Again we know that this term cannot be 0, so we have p lambda to the power 4 plus q lambda square plus r equal to 0. So a polynomial of lambda which is equal to 0. Now we know the solution of this. So this tells us that lambda square is equal to minus b plus minus b square minus 4pr by 2p. Now this, so here we can see two values of lambda square. For plus here I get one value, for minus here I get one value, and again if I take root of this to get lambda, I get two more values. So finally we get lambda 1 equal to, if I take minus sign here, if I take the minus sign, then it becomes q plus q square minus 4 pi r by 2p, and then I have root half to the power half, and if I take the plus value, that means if I take mod of it and I, so this is a complex number, so I get a complex root, and lambda 2 is again just minus lambda 1, so that is another root, and then if I take plus here, and if I say that q square minus 4 pi r is more than q, so lambda 3 is equal to q minus q plus q square minus 4 pi r divided by 2p, that is one root, and then we have lambda 4, that is minus of lambda 3. So here we are assuming that q square minus 4pr is greater than q. Yes, and so this gives us distinct roots, and two roots are complex and two roots are real. Now after that, with this we can write the solution as, so general solution a general solution of this can be written as Wn as a function of x is equal to an cosine lambda 1 x plus bn into sine lambda 1 x plus cn into cosine hyperbolic lambda 1 x plus dn into sine hyperbolic lambda 3x and into sine hyperbolic lambda 3x. Now this is a general solution. So if I want to get the proper solution, the final solution, we have to put the boundary conditions here. So if I assume the fixed boundary condition at x equal to 0 and x equal to a, so this is simply supported, this is simply supported. So let's say it is fixed, or we can call it clamped also. So fixed or clamped at x equal to 0 and x equal to a. That means that at x equal to 0 and at x equal to a, we have w equal to 0, and also we have del w by del x equal to 0. Now this says that for this to be true, we have to have wn equal to 0 at x equal to 0 and a, and also dwn by dx equal to 0 at x equal to 0 and x equal to a, because if I differentiate it, I mean our assumption was w is equal to summation of wn, capital Wn multiplied by sin n pi y by b into e to the power I omega t. So if I differentiate with respect to x, I get summation of dwn by dx multiplied by sin n pi y by b into e to the power I omega t, and that can only be 0 when dwn by dx is 0 at any value of y. So if I put these boundary conditions, so there are now 4 conditions. At x equal to 0, this is equal to 0, at x equal to 0, this is equal to 0, then at x equal to a, this is 0, and at x equal to a, this is 0. So those 4 equations can be written in a matrix form in this way: 1, then we have 0, then we have 1, and then we have 0, then cosine lambda 1 a, and we have sine lambda 1 a, and we have cosine h lambda 3 a, and we have sine h lambda 3 a, and then we have 0 lambda 1, and then we have 0 lambda 3, and then minus lambda 1 sine lambda 1 a, lambda 1 cosine lambda 1 a, lambda 3 sine hyperbolic lambda 3 a, and we have lambda 3 cosine hyperbolic lambda 3 a. So this multiplied by an, a vector of an, bn, cn and dn should be equal to 0. Now here the first equation, this comes from w equal to 0 at x equal to 0. The second equation comes from w equal to 0 at x equal to L. Third equation comes from w equal to 0, del w by del x equal to 0 at x equal to 0, and then the fourth equation comes from del w by del x equal to 0 at x equal to L. Now we have these 4 equations, so let's call it E multiplied by an, bn, cn, dn and that's equal to 0. So we are calling this matrix as E. Now for a non-trivial solution, this determinant of E must be 0. So for non-trivial solution, determinant of E must be 0, and if I set it up, finally these equations are in the form of lambda 1 and lambda 3, and we have seen that lambda 1, lambda 3 are all functions of, if I just go back, all functions of PQR, and PQR are functions of omega square. So in this equation, determinant of E equal to 0, the only unknown is omega or omega square, so from which we can find out the omega. So we can find out so from this omega can be found out. So that's how we find out the natural frequency. Now here we have to do it for each n, and for each n we will get a 4 by 4 equation, and by setting the determinant of this matrix to E to 0, we can get the corresponding values of omegas, and then we can, for each omega, we can put it back in the equation, and we will get A n, B n, C n, D n, and from this we can find out the vibration modes. So once we find out A n, B n, C n, D n, we can put it back in this equation. So that means we can find out Wnx, and then we can put that Wnx back here in the actual assumption, and that will give us the vibration mode. Next is if it is simply supported. So let's say that this is simply supported at x equal to 0 and x equal to b also, and instead of doing a Navier type solution, which is possible because we still want to do a Levy type solution. In that case, the same approach goes. We just have to put the appropriate boundary condition at x equal to 0 and a. So if simply supported at x equal to 0, x equal to a, so in that case we know that the boundary conditions are at x equal to 0 and x equal to a, w is 0, and mx, which is equal to minus dxx del 2w by del x2 plus dxy into del 2w by del y2, that's equal to 0, and this tells us that at x equal to 0 and a, Wn should be 0, also d2wn by dx2 also should be 0, because if I want to take it further, I can write this same expression as dnn with the assumption that we made. So del 2w by del x2 becomes del 2wn by del x2 into sin n pi y by b, and that we can take out, so and write separately, plus dxy wn, and then we have sin n pi y by b e to the power I omega t, and this sum goes from n to 1 to infinity. Now for each n we know that this cannot be 0, so this entire thing has to be 0, and again the other boundary condition says that this has to be 0 at x equal to 0 and a. So for this sum to be 0, this also has to be 0 now, because this is already 0, so this has to be 0, this also has to be 0, then only we can say that this sum is 0. So these are the two boundary conditions we have. Now if we put those boundary conditions, it looks like one 0, 1, 0, and then we have cosine lambda 1a, sine lambda 1a, cosine hyperbolic lambda 3a, sine hyperbolic lambda 3a, 0 minus lambda 1 square, 0 lambda 3 square, and then we have lambda 1 square cosine lambda 1a minus lambda 1 square sine lambda 1a, lambda 3 square cosine hyperbolic lambda 3a, lambda 3 square sine hyperbolic lambda 3a, and then we multiply this with an, bn, cn, dn, and the right hand term becomes 0, 0, 0, 0. Again this has come from at x equal to 0, w is 0. This term has come from at x equal to a, w is 0. This term has come from at x equal to 0, mx is 0, and this has come from at x equal to L, mx is 0. And again we write this equation as E multiplied by an, bn, cn, dn, and the right hand side is 0, 0, 0, 0. And then again the same argument goes, an, bn, cn, bn, cn, dn cannot be 0 if I want a non-trivial solution. So for that E, the determinant of E has to be 0, and E is a function of omega only, so from which omega can be obtained. And then from that omega again an, bn, cn, dn can be obtained, which that gives us the mode shapes. And again please understand that these are an, bn, cn, dn, they gives us the mode shapes. Now in this kind of solution an, bn, cn, dn can have many solutions, so we should get them as a ratio, and then we can be normalized if we want. So this is how we do the Levy's solution for free vibration analysis of a cross ply laminate, where two opposite edges are simply supported, and we have dealt with two cases where the other two edges are clamped and also simply supported. And as we discussed before, this can be a check. Here we initially considered that these two are simply supported, and then later on we put simply supported condition here. We could have reversed it also, so we could have assumed these two first simply supported, and then after getting the fourth order differential equation, ordinary differential equation, we could have put the boundary conditions here, and we can see whether the solutions are coming to be same or not. And also we can try to match these solutions with what we get from the Navier solutions. That can be a nice exercise to work on. So if there are other types of conditions, that is also possible with this kind of approach. So this brings us to the end of this lecture. We will see you in the next class, and we will start with the energy based approach. Thank you.